For this example, we're going to find the derivative, and then once we've found the derivative, we're going to find the equation of the tangent line at the indicated or given value. So a little bit here, this is written w equals g of z. So w is this function g. W is a function g in terms of the independent variable z. So my output is w or g of z. They both mean the same thing. And then my input is z. So, I could see this written two different ways. If it was just written like this, when we calculate the derivative, we would write z or g prime of z. Okay? And we'll calculate our derivative using our formal definition. Now, if this had been given to us and was just written as w, then I would write my derivative, the derivative of w with respect to z. Okay, so I just want you to see those two different notations, and it's not meant to confuse you. It's just to help you understand that they all mean the same thing. So we started with g of z, or we had w equals g of z. I'm just going to put that back, leave that there. So up to now, we only know how to use our formal derivative definition. So I'm going to write that out. In this case, I'm going to write w prime equals, or again, I could write g prime of z. They mean the same thing. G prime of z equals, my formal definition is going to be the limit as h approaches 0 of g of z plus h minus g of z all divided by h. So instead of f, I'm using g for my function, and instead of my normal x, my independent variable is z. So setting this up, I would have, this is equal to the limit as h approaches 0 of, now, z plus h, that is going to be 1 plus the square root of 4 minus z plus h. Notice I've used parentheses in there. All of that minus my original function g of z, and g of z is 1 plus the square root of 4 minus z. All of this needs to be divided by h. So as we work to simplify this, we've got some negatives to distribute. We have radicals. There's a lot going on here. All right, so I'm going to just go at it. We have the limit as h goes to 0. In my numerator, I have 1 plus the square root of 4 minus z minus h minus 1 minus the square root of 4 minus z. So you want to make sure that that minus distributes to the plus sign in front of that, and this minus in front of the z plus h goes to that h as well. All of this is divided by h. All right, so we should notice that plus 1 minus 1 cancels. This leaves us with a rational expression, and we are dealing with radicals, which oftentimes means we're going to end up using a conjugate. So I have 4 minus z minus h minus the square root of 4 minus z, all of which is over h. So at this point, our strategy, especially when we have radicals, square roots, is we multiply by 1 and we form that 1 by using the conjugate. So that's 4 minus z minus h, and this would be plus the square root of 4 minus z. Now, it's okay for me to multiply that as long as I put it over itself, which means I am multiplying by 1. Now remember, when we FOIL in the numerator, we're going to multiply that all the way out to get rid of some of those radicals. But in the denominator, we almost always leave the denominator in factored form. So when I look at multiplying this, my first term is going to be a square root squared, which essentially means that's going to be canceled. My inner and outer terms as I multiply, those are going to be the opposite of each other, so they're going to go to 0. And then my last term, it's going to be the same quantity squared, but a negative times a positive. It's going to make sure that or let us know that we have a negative result here. So what does this look like? The limit as h approaches 0 of, I would have 4 minus z minus h minus 4 minus z. And all of that is over h times the quantity square root 4 minus z minus h plus the square root of 4 minus z. So it should be easy for you to multiply, to FOIL all of this and create that numerator. All right, but you, if you need to, pause the video, practice, make sure you can come up with this next line. And you're always going to notice when you're multiplying these conjugates, okay, conjugate plus and minus, they have opposite signs in the middle of those two terms. When you're doing that, you're always going to, if you've got square roots, that square root's going to go away in both of those. So you're going to see a pattern here. All right, so looking at what we have in order to continue simplifying, 4 minus 4 is going to go away, and negative z minus negative z, that's plus z. This leaves me with, I have the limit as h approaches 0 of negative h over h times the square root of 4 minus z minus h plus the square root of 4 minus z. And you'll notice I have a times h in the numerator, a times h in the denominator. That's going to leave me with a 1 in my numerator. So I have the limit as h approaches 0 of negative 1 over the square root of 4 minus z minus h plus the square root of 4 minus z. So once we cancel this h value, that was that initial h in the denominator, once we cancel that, we're normally good to go at evaluating our function when h equals 0. In this situation, if I plug my 0 value in for h, I'm going to end up with negative 1 over the square root of 4 minus z minus 0 plus the square root of 4 minus z. So 4 minus z minus 0, I don't need that 0 there. So really, I have the square root of 4 minus z plus the square root of 4 minus z, which is negative 1 over, if I'm adding those, I have 2 square roots of 4 minus z. So this represents my derivative. G prime of z, or w prime, or the derivative of w with respect to z, they all mean the same notation. What that's equal to is negative 1 over 2 times the square root of 4 minus z. So this is my derivative. All right, I'm not done with my problem yet, but we have found the derivative. So remember, there was a second part to this problem. It said once you find that derivative, we need to write the equation of the tangent line at the indicated value. All right, so I'm going to go to the next page. So let's look at what we have here. I've rewritten my function. I have a point, an input value, and then I have my derivative. And we need to write the equation, write that equation of the tangent line. All right, so we got to write the equation of the tangent line. In order for us to do that, to write the equation of a line, we need a point and a slope. So in order to find the point, we're going to make sure that we use our original function. So w equals 1 plus the square root of 4 minus z. In this case, w equals 1 plus the square root of 4 minus 3, which is 1 plus the square root of 1, or 2. So I know I have an ordered pair, 3, 2. That is equal to zw. And we're just using z and w instead of x and y in this situation. All right, so now I have a point. I also need a slope. And the slope is always going to come from the derivative. So g prime of that 3 value, the 3 coming from the z, is negative 1 over 2 square root of 4 minus 3, which is negative 1 over 2 times the square root of 1, or negative 1/2. So what does that mean? Let's interpret that. G prime of 3 means the rate of change at z equals 3, or x equals 3. The rate of change at z equals 3, my slope, is negative 1/2. Okay, so the slope at z equals 3, we've got m equals negative 1/2. So remember that point, the ordered pair, is always going to come from the original function, and the slope comes from plugging that value into the derivative. All right, so if we need to write the equation of this tangent line, I would say y minus, my y value in this case is w, or 2, equals m negative 1/2 x minus, and my z value is 3. All right, so we have y minus 2 is negative 1/2 x plus 3/2, and I would add that 2 to both sides of the equation. Y equals negative 1/2 x plus 3/2, positive 3/2 plus 2, which is 4/2, gives us 7/2. So my equation could be written like this. If I wanted to use the same variables that were given, that would be w equals negative 1/2 z plus 7/2. All right, and so looking at this, just keep in mind I did y minus y1 equals m times x minus x1. That's my point slope equation. And if we were thinking about connecting these concepts, looking at our graphing calculator, my original function is square root function, shifted right 4 units, up 1 unit, and reflected horizontally over the y-axis. And on this graph, I have the point, that ordered pair that we found, 2, 3. And if I were to look at graphing my tangent line, it would have a slope of negative 1/2, would touch right there, and we'd have this y-intercept at 0, 7/2. So I hope that kind of helps you understand it a little bit better. Again, please email me if you have any questions. In this video, we found the derivative using the definition of a derivative of a radical function, and then we found the equation of the tangent line.